One ship, 10 tankers minimum, arriving one by one, 1,200 tons of propellant that exists as a liquid only as long as it stays cooled enough. A departure window that opens for 97 days every 26 months and does not negotiate. A fluid that begins converting to gas the moment solar radiation touches the tank. The most capable rocket ever built cannot reach Mars until it solves a problem that happens before it leaves Earth orbit, transferring more than 1,000 tons of fluid that is continuously trying to become a gas in an environment where liquid and gas do not separate, with a departure window that closes on a schedule the Sun and the solar system set, and no engineering decision can move. Speed up the transfer sequence to beat the Boiloff losses and the operational tempo, 10 docking operations in rapid succession, each requiring orbital rendezvous between two vehicles traveling at 28,000 kilometers per hour, compounds the probability that one of those operations encounters the microgravity fluid behavior anomaly that interrupts a transfer mid-operation and adds days to the sequence. Slow down and add active cooling to minimize boil-off during an extended sequence, and the mass and power infrastructure required for zero boil-off storage in orbit has never been demonstrated for a week, let alone the duration the architecture requires, and the cooling system becomes the single mechanical component whose failure strands the entire mission while the departure window counts down. The mission needs to be fast enough to beat the boil-off and careful enough to avoid the fluid anomalies, and those two requirements pull the timeline in opposite directions simultaneously inside a window that moves on its own schedule, regardless of which constraint wins on any given day. Most coverage of Starship focuses on what happens after the departure burn, the transit to Mars, the landing, the surface operations, the prospect of a permanent colony. The sequence that determines whether the departure burn ever happens is the one the renders skip. The renders show Starship in orbit, then Starship en route to Mars, cutting past the 10 to 15 tanker arrivals, the docking operations, the cryogenic transfers, and the multi-week thermal management problem that sits between those two frames. The skip is understandable. A render of a propellant transfer is less compelling than a departure burn, but it represents the gap between the system's engineering ambition and the constraint that currently defines its critical path. The propellant that Starship uses is liquid oxygen and liquid methane. The choice is deliberate and well-reasoned. Methane is manufacturable from carbon dioxide and water using processes that work on Mars, which means a ship that departs Earth with methane-oxygen engines can theoretically refuel at the destination rather than hauling return propellant from Earth. This closes the logistics loop that makes Mars colonization economically conceivable. The same properties that make these propellants attractive for an interplanetary mission make them physically difficult to manage in orbit. Liquid oxygen exists at minus 183 degrees Celsius, cold enough that the difference between keeping it liquid and watching it boil is measured in the thermal load from a single surface in direct sunlight. Liquid methane is marginally warmer at minus 161, but shares the same fundamental problem. Both fluids are at temperatures so close to their boiling points that any heat input from the environment drives continuous conversion from liquid to gas. On Earth, managing this is straightforward. Gravity keeps the liquid at the bottom of the tank and the gas at the top. The pump inlet sits below the liquid surface, drawing from a settled single-phase fluid. Pressure management vents gas from the top while keeping the liquid column intact. The thermal challenge is real but manageable with insulation and active cooling. In low Earth orbit, gravity is effectively absent. The liquid and gas inside the tank do not separate. They form a mixture that moves based on the vehicle's acceleration, the pressure gradients inside the tank, and the surface tension of the fluid against the tank walls. A pump trying to draw liquid from that environment may pull liquid, may pull gas, or may pull a mixture that interrupts flow unpredictably. The behavior cannot be fully predicted from ground tests because the fluid dynamics of a cryogenic two-phase mixture in a tank undergoing orbital freefall is not reproducible in a ground-based laboratory at full scale. Settling the fluid, creating enough artificial gravity inside the tank to push the liquid toward the pump inlet, requires firing a low-thrust engine to accelerate the vehicle gently in one direction while the fluid redistributes under the resulting pseudogravity. This works, and the technique has been used in spacecraft propellant management for decades. Each settling burn consumes propellant. During a transfer operation between two docked vehicles, coordinating settling burns requires both vehicles to maneuver together without stressing the docking connection. The connection that allows propellant to flow between the two vehicles must handle cryogenic temperatures, the differential thermal expansion between materials at those temperatures, and the mechanical loads of two large vehicles adjusting their orientation in space simultaneously. No component in that interface has been tested in orbit at the scale Starship's transfer architecture requires. In 2023, NASA's Independent Review Board published its assessment of the Artemis Human Landing System program, which uses a variant of this architecture for a lunar mission, requiring fewer tanker flights than a Mars mission and a shorter orbital stay. The board identified in-orbit cryogenic propellant transfer as the single highest-risk undemonstrated technology in the entire program. The specific language was precise. SpaceX had not conducted a single orbital cryogenic propellant transfer test of any kind at the time of the review. The 10 to 15 flight requirement for a Mars mission represented an operational complexity that had no precedent in the history of spaceflight. The board's findings were published in a document available to anyone who looked for it. The Starship integrated flight test that occurred the same month generated substantially more coverage. The boil-off rate for liquid oxygen in an orbital tank without active cooling is roughly 3 to 0.5% of total propellant mass per day, a figure that sounds small and is not at the scale Starship's architecture requires. 0.3% of 1,200 tons is 3.5 tons per day. Across a 10-day refueling sequence, passive boil-off losses approach 35 tons, more than the payload capacity of most rockets currently operating. The mission architecture must account for these losses by over-delivering propellant across the tanker sequence, which requires additional tanker flights, which extends the sequence duration, which increases cumulative boil-off, which may require yet another tanker flight. The loop does not diverge to infinity, but it also does not converge to zero. It settles at a loss budget that the architecture must incorporate and that grows with any extension of the orbital transfer timeline. You are the Mission Operations Director for the third tanker delivery in the refueling sequence. Tanker 1 and Tanker 2 completed their transfers within the planned parameters. Tanker 3 has docked and the transfer has begun. 40 minutes into the operation, the flow rate sensor on the receiving ship's oxygen tank drops to zero. The transfer line is pressurized. The pump is running. Gas ingestion at the tanker's pump inlet has interrupted the liquid flow. The tanker must detach, perform a settling burn to re-establish a liquid-vapor interface at the pump inlet, reapproach, redock, and resume the transfer. The reapproach sequence takes 3 hours. The receiving ship's tanks absorbed solar radiation for those 3 hours without a transfer flow to offset the thermal load. The pressure in the receiving ship's oxygen tank has risen to the relief valve threshold. The valve opens. A fraction of the propellant you have already transferred vents as gas into the space around the docking interface. The sequence continues, but the boil-off clock has been running longer than the architecture's loss budget assumed, and you still have 7 tanker flights remaining. The engineering response that addresses the boil-off problem without extending the transfer timeline is a dedicated orbital propellant depot, a permanently stationed cryogenic storage facility in LEO equipped with active cooling, large tank volumes, and purpose-built transfer systems. Tankers deliver propellant to the depot over weeks or months before the mission. The depot aggregates and maintains the stored propellant with active zero boil-off cooling, and the departing ship receives a single high-rate transfer from the depot in a compressed time frame. The proposal reduces the number of sequential docking operations the departing ship must complete before departure, and reduces the departure ship's total time in orbit with open tanks. The depot concept addresses the boil-off problem and introduces a different constraint. No zero boil-off cryogenic storage system has been demonstrated in long-duration orbital operation. Active cooling in orbit requires power, continuous power, from solar arrays that must maintain orientation relative to the Sun while the depot maintains orientation relative to its own operational requirements. The cooling system itself has moving parts, compressors, heat exchangers, fluid loops. Any mechanical failure in the cooling system initiates boil-off in the depot's tanks, and the depot's tanks contain the entire propellant load for the mission. A micrometeorite impact on a cooling system component, a power anomaly that interrupts cooling for hours, a seal failure in a cryogenic fluid loop, each of these is a low probability event on any given day. Across months of continuous operation, the probability accumulates. The depot that was designed to eliminate the sequential tanker risk concentrates the mission's entire propellant dependency into a single orbital asset whose loss ends the mission completely rather than delaying it. The 97-day departure window is the constraint that none of the engineering solutions for boil-off or fluid management can expand. Mars and Earth reach a favorable orbital geometry for a minimum energy transfer trajectory once every 26 months, and the window in which the geometry supports departure stays open for less than 100 days before the required propellant mass for the transit begins to climb steeply enough to exceed what even a fully fueled Starship can carry. Miska window, due to any combination of tanker delays, boil-off losses, fluid management anomalies, or depot failures, the fully loaded ship in orbit faces a choice with no good branch. Depart with a reduced propellant margin and accept a transit trajectory that requires more propellant mid-course than the architecture planned for, or hold the ship in orbit for 26 months and maintain cryogenic storage for the entire interval with the same systems that have not been demonstrated for a fraction of that duration, waiting for the next window while every day in orbit is another day of thermal loading, another day of boil-off, another day of mechanical system exposure to the radiation and temperature cycling of low Earth orbit. The propellant that makes Mars colonization logistically conceivable, manufacturable at the destination, energetically efficient, cheap to produce, is the propellant that requires this entire operational infrastructure to get off Earth. A different propellant choice could simplify the orbital transfer problem. Storable propellants, fuels that exist as liquids at room temperature and have no boil-off problem, are manageable in orbit without active cooling, without boil-off budgets, without thermal management infrastructure. They were used in every lunar mission of the Apollo era and every interplanetary mission since. A Starship architecture using storable propellants would not face the cryogenic thermal management problem at the departure stage. It would face a different terminal problem at the arrival stage. Storable propellants cannot be manufactured on Mars, which means every Mars mission using them must carry return propellant from Earth or accept a one-way architecture, and the propellant mass required for a return mission using storables makes the launch mass budget unworkable at any vehicle size that current launch infrastructure can lift. The choice is not between a propellant that works in orbit and one that works on Mars. It is between a propellant that creates the problem at Earth and one that creates it at Mars, and the architecture chose the version where at least one of the two problems has a theoretical manufacturing solution at the destination. SpaceX's Starship development program includes orbital refueling demonstration as a stated near-term milestone. The specific test, a cryogenic propellant transfer between two Starship vehicles in low Earth orbit, has not been conducted as of the most recent publicly available program status. The Artemis timeline that depends on demonstrating this capability before a human lunar landing has shifted multiple times, with in-orbit refueling demonstration consistently appearing as a prerequisite that must precede crew missions. The gap between the first Starship integrated test flights and the first orbital cryogenic transfer test is not a gap between ambition and competence. SpaceX has demonstrated engineering capability at a pace that has surprised every analyst who predicted it could not. The gap is between the launch demonstration and the thermal management demonstration, and those are different physics problems requiring different test campaigns. A Mars departure window opens for 97 days. The first tanker arrives. The boil-off clock starts. The engineering that has been tested on the ground encounters the environment it was designed for. Whether the 1,200 tons needed in the tank are there when the window peaks, or whether they are partially in the tank and partially vented into low Earth orbit as gas, depends on a sequence of fluid dynamics outcomes that the orbital test campaign will resolve. That campaign has not started. The window does not wait.